The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Okay, to work. A word of warning. Fasten your seatbelts. Or another way of saying it is I'm going to open up the fire hose a little bit today. Last lecture, you might have thought this was a SHAS class. It sounded like a philosophy class. And it was important to set the stage for what we're going to talk about. But we talked about very high-level things. The notion of recipes, the notion of computation, why you want to do this, what you're going to learn. Today, we're going to dive into the nitty-gritty, the nuts and bolts of the basics of computation. And in particular, what I'm going to do today is I'm going to talk about operators and operands, which we did a little bit last time, in particular how to create expressions. I'm going to talk about statements as the key building blocks for writing code. And I'm going to introduce simple sets of programs. In particular, I'm going to talk about branching, conditionals, and iteration. So a lot to do. Okay? So let me jump straight to it. At the end of last lecture, we started introducing some of the pieces we want to do. And I want to remind you of our goal. We're trying to describe processes. We want to have things that deduce new kinds of information. So we want to write programs to do that. If we're going to write programs, we need at least two things. We need some representation for fundamental data. And we saw last time two examples of that. And the second thing we're going to need is we're going to need a way to give instructions to the computer to manipulate that data. We need to give it a description of the recipe. In terms of primitive data, what we saw were two kinds, right? Numbers and strings. A little later on in the lecture, we're going to introduce a third kind of value. But what we're going to see throughout the term is no matter how complex a data structure we create, and we're going to create a variety of data structures, fundamentally all of them at their basis, their atomic level, if you like, are going to be some combinations of numbers, of strings, and the third type, which are Booleans, which I'm going to introduce a little later on in this lecture. And that kind of makes sense, right? Numbers are there to do numeric things. Strings are our fundamental way of representing textual information. And so we're going to see how to combine those things as we go along. Second thing we saw that associated with every primitive value was a type. And these are kind of obvious, right? Strings are strings. For numbers, we had some variations. We had integers, we had floats. And we'll introduce a few more as we go along. But those types are important because they tell us something about what we want to do when we want to put them together. Okay, but nonetheless, I want to stress we have both a value and a type. All right, once we have them, we want to start making combinations out of them. We want to put pieces together. And for that, we combine things in expressions. And what we saw is expressions are formed of operands and operators. And the simple things we did were the sort of things you'd expect from numerical things. Now, I want to stress one other nuance here, which is, and we're going to do some examples of this. Initially, we just typed in expressions into the interpreter, that is, directly into Python. And as I suggested last time, the interpreter is actually a program inside of the machine that is basically following the rules we're describing here to deduce the value and print it out. And if we type directly into the interpreter, it essentially does an eval and a print. It evaluates and it prints. Most of the time, we're going to be doing expressions inside of some piece of code, inside of a script, which is the Python word for program. And there, I want to make this distinction, this nuance. The evaluator is still going to be taking those expressions and using its rules to get a value, but it's not going to print them back out. Why? Because typically you're doing that to use it somewhere else in the program. It's going to be stored away in a variable. It's going to be stuck in a data structure. It's going to be used for a side effect. So inside of code or inside of a script, there's no print unless we make it explicit. And that's a little bit down in the weeds. It's a detail, but one I want to stress. You need to, if you want something to be printed out inside of your code, you need to tell the machine to do that. Okay. So let's do some simple examples. We've already seen some of these. I just want to remind you, if I want to, for example, type in an expression like that, notice the syntactical form. It's an expression, a number, followed by an operand, followed by another expression. And of course, I get out the value I'd like there. Yes, sir? Oh, you don't like leaning that far to the left? Okay, if you're a Republican, I'll be happy to shift this over a little bit. Wow, John, I got to laugh for a political joke. I'm in big trouble. Is that better? Oh, damn. All right. I'll do it even more. Okay, here we go, here we go. See, I'm doing it down here. I can't see it. Does that, I hear a sighs of relief. Okay, good. There we go. Better. All right. One of the other things we showed last time is that operators are overloaded. And this is where you heard John and I disagree. I don't happen to like this, but he thinks it's an okay thing. And in particular, if we don't do that, we do this. That is, give a combination of a number, multiplication, and a string. This will, in fact, give us back a new string with that many replicas, if you like, of the string concatenated together. Right? And if we want to do other things, for example, we can take two strings and add them together. And we'll get out, again, a concatenation of that string. And these will let you work through the variations, but these are the simple expressions we can use. Now, sometimes things get a little interesting. Right? What's the value of that expression? What do you think should happen if I evaluate that expression? Somebody with a hand up so I can see it. What's going to happen? An error. Why? Great. Okay. Let's just check it. It certainly is. We bribe people. So, by the way, John's a Yankees fan. He throws like Johnny Damon. I'm a Red Sox fan, so we'll see if how about that? And I almost hit John along the way. Great. I thought, right, exactly. What can I say? All right, so we're into bribing you as we go along here, all right? You'll be badly overweight by the end of the term. Right, it's a syntactic error because it doesn't know how to deal with this. But there's an important thing going on here. If I, in fact, wanted to combine those into a string, I should have told the machine to do that, and I can do that by explicitly saying, take that which is a number and convert it into a string, and then, I keep doing that, then add it to that string. Okay, so there's an important point here. We've got what's called type conversion. That is, if I want to combine two things together in a particular way, I need to make sure that I give it the kind of operand it expects. So str, which I just typed up there, takes in parens some input, and it converts it into a string so that now I can use that where I was expecting a string. John?
Technically speaking, that's a static semantic error.
Thank you.
Not a syntactic error.
And I was going to come to that in a second, but thank you, John, for pointing it out. Right? Why is it a static semantic error? The syntax is okay in the sense of it is an operand, an operand, an operator, an operand. So syntactically it's okay. The semantics was what caused the problem because the operator was expecting a particular kind of structure there. There's a second thing going on here that I want to highlight because it's really important. Yes, indeed. Okay, there we go. The second thing I want to highlight is that what's going on is that Python is doing some type checking. It caught the error because it checked the types of the operands before it applied things, and it says, I'm going to stop. Now, you might have said, gee, why didn't it just assume that I wanted to, in fact, treat these as strings and combine them together? Sounds like a reasonable thing to do, but it's a dangerous thing. Because in doing that, Python would then have a value that it could pass on into some other part of a computation, and if it wasn't what I wanted, I might be a long ways downstream in the computation before I actually hit some result that makes no sense. And tracing back where it came from can be really hard. So I actually want to have type checking as much as I can early on. And in fact, under type checking, different languages sometimes fall on a spectrum from weak to strong typing, which basically says how much type checking do they do. Now, you're going to hear John and I go back and forth a lot. As I said, I'm an old-time, well, I'm certainly old-time, but I'm also an old-time Lisp programmer. I love Lisp, but Lisp is certainly in the category of a very weakly typed language. It does not check the types of its arguments at all. Python is, I wouldn't say completely strong, but it's much closer to the strong end of the spectrum. It's going to do a lot of type checking for you before it actually passes things back. Nonetheless, I'm also going to argue that it's probably not as strongly typed as we might like. So, for example, there's an expression. Now, less than is just, if you haven't used it before, is just the operator you'd expect. It's comparing two things, and it's going to return either true or false, depending on whether the first argument is less than the second argument. What's going to happen here? Again, I need a hand so I can know where to throw candy. Also got my reading glasses on. I can't see anything. Anybody? TAs don't count. They get their own candy. Yeah. Good question. Sounds like a reasonable guess, right? How in the world am I going to compare a string to a number? So, see how good my aim is? Not bad, all right? A good thought, but in fact, son of a gun. Or as my younger son would say, fudge knuckle. Yeah, all right? So what in the world's going on here? This is a place, I don't know about you, John, I think this is actually really not good. Because, right, what this is doing is it's allowing, sorry, let me back up and say it. It's got an overload on the less than that allows you to compare basically the lexicographic ordering or the sequence of ordering of symbols, including numbers inside of the machine. And this, in my mind, should have been an error. I mean, why in the world would you want to compare that? Just to give you an example of that, for instance, I can do the following. Right? The number 4 is less than the string 3, whereas the string 4, is not less than the string 3. And this is a place where it's comparing strings and numbers in a strange way. So why am I showing you this? Partly to show you that it's kind of weird, but also to tell you that one of the things you want to do is exercise what I'm going to call some type discipline. Meaning, when you write code, you want to get into the habit of A, checking out operators or procedures to see what they do under different circumstances. Either check them out or read the specifications of it. And 2, when you write your own code, you want to be disciplined about what types of arguments or operands you apply to operators. Because this is something that could certainly have screwed you up if you didn't realize it did it. Okay? And you need to have that discipline to make sure it's doing the right thing. Okay. One of the other things you're going to see is that some of the operators have odd meanings. And again, I think we look... Yep.
So the string A is less than 3 is false because they're comparing like ASCII values?
Yes.
Okay.
I mean, the answer is, I don't know if it's ASCII. John, do you know, are they doing ASCII encoding inside of here? I'm assuming so. Yeah. Right, so in case you didn't understand what the question was, basically every symbol gets translated into a particular encoding, a string of bits, if you like, inside of the machine. There's a particular one called ASCII, which is, if you like, an ordering of that. And that's what the machine's actually comparing inside of here, which is why under ASCII encoding, the numbers are going to appear after the characters. And you get this strange kind of thing going on. All right, I want to do a couple of other things, just to quickly remind you. One of them is, remember, the operators do look at the types. So division, for example, 9 divided by 5 is 1, because this is integer division. That is, it's the largest number of integer multiples of 5 that go into 9, and there would be a remainder associated with it, which is, in fact, 4. And again, you've got to be careful about how you use the operators. All right, having done that, we can certainly get to more complicated things. So, for example, suppose I look at that expression, 3 plus 4 times 5. All right, now, there are 2 possible values here, I think. One is 23, the other is 35. Because this could be 3 plus 4 times 5, or it could be 3 plus 4 times 5. And of course, you know, when you look at code, it doesn't pause in between them. But what did I do? I just separated. Do I do the addition first or do the multiplication first? Anybody know what happens in this case? Yeah, way up. Oh, God, I'm going to have a hell of a time throwing up there. Way up at the back.
Standard order of operations, PEMDAS, I guess, it'll take the multiplication first and then add the 3.
Right. I'm going to try. If I don't make it, you know, just get somebody to pass it back. Whoa, I just hit somebody in the head. Thank you. Please pass it back to that guy. If you want candy, sit much closer down, and that way we can film you as well as we go along. All right, so the point is there is something here called operator precedence, which is what the gentleman said. And I'm not going to say much more about it, but basically what it says is, with all other things being equal, things like exponentiation are done before you do multiplication or division, which are done before you do things like addition and subtraction. And so, in fact, if I wanted the other version of it, in fact, if I do this right, it's going to give me 23 because it does the multiplication first. If I wanted the other version of it, I need to tell it that by using, parentheses. And in general, what I would say is, when in doubt, use parens. Okay. Now, that just gives us expressions. We can start having complex expressions. You can imagine we can have things with lots of parens and all sorts of things in it. Yes, question?
What is the operator used when you were calculating remainder between 9 and 5?
It's the percent sign.
Oh, thank you.
If you can't read it, and I guess I'm going to have to blow that font up, aren't I, next time around? Yes, the percent. So it's percent sign will give you the remainder. Okay. Second thing I need to do, though, is I need to, when I get those values, I want to hang on to them. I'd like to give them a name so I can refer to them in other places. And so we saw that as well. The last piece we had here was the ability to create variables, which have their own values. And that's done using an assignment statement. So in particular, that is an assignment statement. It says take the name x and create a binding for that name to the value of the sub-expression. And in fact, to do this, to stress a point, let's do that. It's not just a number, it's any expression. What Python will do is it will evaluate that expression using the kinds of rules we talked about, and then it creates a binding for x to that value. And I want to stress this. We're going to come back to it later on in the term. So the way I'd like you to think about it for now is that somewhere in the machine there's a big space that contains all possible values. Right, it's a slight lie. It doesn't have all possible values, but you get the idea. It has, if you like, intellectually all possible values. And when I create a binding, I'm taking a variable name, in this case x, stored somewhere in a table, and I'm creating a link or a pointer from that name to that value. This is a nuance. It's going to make a lot more sense later on when we introduce mutation into our language, but I want you to start thinking of that way. Don't think of it as a specific box into which we're putting things. Think of it as a link to a value. I could have, for example, another assignment statement, and that creates a binding from y into that same value. And one of the things as a consequence I can do is I could have a statement like, let z be bound to the value of x. And I said it deliberately that way. That statement says get the value of x, which is this link, and give z a pointer to the same place, to the value, not to x. Okay, now I want to just plant that idea. We're going to come back to it later on as we carry on. Okay, so if we have variables, one of the questions we can ask is, what's the type of a variable? And the answer is it inherits it from its value. Okay? It gets. So if somewhere in my code I have that statement, that assignment statement, x now is a variable whose value is an integer. Unfortunately, at least in my mind, in Python, these variable bindings are dynamic. Or the type, rather, is dynamic. Meaning, it changes depending on what the current value is. Or said a different way, if somewhere later on in the program I do this, x now has changed its type from int to string. Now, why should you care? Again, my view is I don't like it, especially in the presence of operator overloading. Because I might have written some code in which I'm expecting a particular variable to have an integer value. If somewhere later on in the code it shifts to string, I might now be manipulating that, getting actual values out, but not what I wanted. And it's going to be really hard for me to chase it back. So one of the things I would like to suggest is that you develop some good style here. And in particular, don't change types arbitrarily. arbitrarily. I can't spell today. Meaning sometimes you need to do this, but in general, this, at least in my view, I don't know, John, would you agree? You just don't want to do this. You don't want to make those changes. It just leads to trouble down the road. Okay. Now, last thing about variables, and then we're going to start pushing on this, is where can you use them? And the answer is you can use a variable anywhere you can use the value. So any place it's legal to use the value. Okay. Now, this is just sort of bringing us back up to speed and adding a few more details in. What we really want to do now, though, is start using this stuff. So, operands let us take expressions, get values out. We can store them away in places, but ultimately we want to do something with them. So we need to now start talking about what are the things we can do inside of Python or any programming language to manipulate them. And for that, we're going to have statements. Statements are basically, if you want to think about it, legal, and I was about to use the word expression, except I've misused that elsewhere. So legal commands that Python can interpret. And you've already seen a couple of them. Print, assignment. Certainly two obvious statements. They're commands to do something. Assignment is binding a name to a value. Print is saying put it back out on the screen. Obviously, if you have print as a way of putting things out, we expect to have ways of getting input in. We're going to see an example of that in a second. And as we go through the next few lectures, we're going to add in more and more of these statements. But let's look at what we could do with this, okay? And to do this, I'm going to use some code that I've already typed in. So I'm hoping you can read that, and it's also on your handout. This is a little file I created, all right? And I'm going to start with a sequence of these things and walk them along. Again, I invite you to put comments on that handout so that you can follow what we're going to do. All right? So let's look at the first part of this. Right now, this is just a text file. Okay, and I've highlighted in blue up there sort of the pieces I'm going to start with. And what do I have? I have a sequence of commands. I've got an assignment statement. I've got another assignment statement. I've got a print statement. I've got an input statement, which we'll come back to in a second. And I want to basically try and use these things to do something with them. Second thing I want to note is the little hash marker, the pound sign, that's identifying a comment. So what's a comment? It's words to you or to the reader of the code that are telling you what's going on inside of this code. Okay? Now, these comments, frankly, are brain damaged or computationally challenged, if you prefer. Meaning, why in the world do I have to tell the reader that I'm binding x to the value 3? All right, I'm putting them in there to make a point. In general, good programming style says you put in comments that are going to be valuable in helping you as a reader understand what's going on inside of the code. It could be what's the intuition behind this piece of code. It could be preconditions I want to have on input. It could be explanations of specific things you're doing. But you need to have those comments there. Now, this becomes a little bit of one of those motherhood and apple pie kinds of lectures. You know, your mother always told you to eat Brussels sprouts because it was good for you. Well, this is a Brussels sprouts comment. Everybody goes, yeah, comments, of course we're going to do comments. And they never do. So my challenge to you, and I know Professor Gotay can do this, my challenge to you is, a year from now, come back and look at code you wrote here. Can you still understand what it was you were trying to do? I don't know, John, if you'd agree, right? If you can read the code a year later, even code you wrote yourself, it's a good sign that you put good comments in, right? Second good piece of style here is choice of variable names. These are lousy, deliberately, okay? I'm just using simple things like x and y and z because I want to just get through the lecture if you like. But in general, the choice of variable name is a great way of commenting your code. Use variable names that make sense. That little problem set 0 that you did. You read in a couple of values, you probably stored them away. My bet is you used simple names like x and y. Much better name would have been first name, last name as the name of the variable to tell you what you were trying to capture there. Okay, the other piece I want to say about variable names is once I have that choice of variable name, I can use it, but in fact there are a few things that I can't use in terms of variable names. So, These are an important way of documenting but there's some things excluded. And in particular, there are some keywords that Python is going to use that have to be excluded. And let me highlight that. As I said, right now that's just text file. I'm going to save this away. Not that way. I'm going to save this away with the subscript, or the suffix rather, py to make it a Python file. And I know it's already there, but I'm going to do it. And I get some wonderful colors. But these are important. Okay? So notice what I have up there now. Comments appear in red. I can see those. There's a keyword, which I'm going to highlight right up here, print, which is, and I don't know what that color is, orange. There's a function in purple. There's a string in green. And in black, I have the assignment statements. That print is a keyword. It's a command to Python to do something. As a consequence, I can't use it as a variable name. Right? Think about it for a second. If I wanted to use print as a variable name, how do I get the system to decide, gee, do I want print as a value for something, or do I want print as a command? So there's a sequence of these that are blocked out. And John, I think, what, 28? Something like that? TAs, is that right? 28 keywords that are blocked? We'll find them as we go along. Okay. Having done this now, I can simply go ahead and run this. And in fact, if I go up here to run, you'll see I've got both an option to check the module, or in this case, I'm just going to run it. Oh, notice what happened. It ran through that sequence of instructions. In particular, it bound x to the value 3. And then it took x times x, got the value of x multiplied by x, which of course is 9, bound that to the value of x. And then it printed out the value. And now it's sitting here waiting for an input. And notice what it did. It printed out that little. Right up here, I'd said enter a number, and that's what it's printed out. So I can enter a number, and it prints it out. Great. Let's run it again. Actually, for that, I can just use, if I'm lucky, function F5, which didn't work, so let me try it again. Here we go. We're going to run that module. Okay. Whoa. What happened? I said enter a number. I didn't. I gave it a string. And it still took it and printed it out. Well, this is one of the places where I want to come back to that highlighting of what do things do. Even though my statement said enter a number, in particular, raw input here simply takes in a set of characters and treats it as a string, and then prints it back out. So if, in fact, I wanted to make sure this was a number, I should have done something like either try and convert it to a number, which, of course, failed here, or put in a check to say where it is. So it's a way of reminding you I've got to be careful about the types of things that I put in. Okay. This is still boring, so let's step on the accelerator. What I have now is the following. I can write expressions, do combinations of things to get out values. I can store them away. I can print them out. But literally all I can do at this stage is write what we would call a straight line program. That is a program in which we execute the sequence of instructions one by one. Simply walk down that list. That's what we just did there, right? We just walked through that list. This is boring, right? In fact, you can do some nice things to prove what is the class of functions you can compute. Yeah, you can compute with straight line programs, and what you'd see if you did that is it's not particularly interesting. Okay? Let's go back and think about our recipes, what we use as our motivation here. Even in real recipes, you have things like, if needed, add sugar. That's a decision. That's a conditional. That's a branch. That says if something is true, do something. Otherwise, do something different. So to really add to this, we need to have branching programs. What I mean by that is a branching program is something that can change the order of instructions based on some test. And that test is usually a value of a variable. Okay? And these get a whole lot more interesting. So let's look at a little example, and this is going to, both allow us to introduce the syntax as well as what we want to have as the flow of control inside of here. So let me go back up here. I'm going to comment out that region. And let's uncomment this region. I want to write a little piece of code that's going to print out even or odd, depending on whether the value I put in, which is x in this case, is even or odd. Think about that. That says if this thing has some particular value, I want to do one thing, otherwise I want to do something different. And let's look at the syntax of this. This is the first of the conditionals that we're going to see. And notice the format. I'm going to go up there. The first statement right here, that's just an assignment statement. I'm giving some value to x. We can make it something different. And then notice the structure here, the next three statements. First of all, if is a keyword, which makes sense. It is followed, as you can see there, by some expression, followed by a colon. And in fact, that colon is important. So let me stress this over here. Right. That colon is important. It's defining the beginning of a block of instructions. Yes, sir? Based on a test, usually the value of a variable. Okay, so let me go back to where I am. I'm looking at that piece of code. What that colon is saying is, I'm about to begin a sequence of instructions that I want to treat as a block. So it identifies a block of instructions. And in particular, the colon is the start, and the carriage return is the end. Now, what in the world does that mean? I'm doing a lot of words here. Let me try and say this a little bit better. That code says the following. The if says, I've got an expression. I'm going to evaluate it. If that value is true, I want to do a set of things. And that set of things is identified by the sequence of commands that are indented in this one right here, following the colon, but before I get back to the same place in terms of the indentation. If that test is not true, I want to skip this instruction, and there's a second keyword, else, followed by a colon. And that tells me the thing I want to do in the case that it's false. So in fact, if I run this, I'm going to save it, and it prints out odd. So what happened here? Well, let's look at the code. All right? X is initially bound to 15. I get to the if. The if says evaluate that next expression. And that next expression, I'm actually taking advantage of the fact that I'm doing integer multiplication and division here. Right? That divide is going, if x is an integer and 2 is an integer, what's it going to do? If x was even, x divided by 2 is going to be actually the half of x, right? If x is odd, that integer division is going to give me the number of multiples of 2 that go into x plus a remainder, which I'm going to throw away. In either case, I take that value and multiply back by 2. If it was even, I get back the original number. If it was odd, I'm not going to get back the original number, so I can just check to see if they're the same. Okay, so a little nuance that I'm using there. So first thing that if does, that if says is evaluate that expression, and if it's true, do the next thing, the thing after the colon. In this case, it's not true, so it's going to skip down and evaluate the thing that printed out the odd. Okay, yes? Thank you. I was hoping somebody would ask that question. Question was, if you didn't hear, why do I have two equal signs? Looks like I'm doing this, right? Anybody have a sense? Why don't I just use an equal sign? I want to know if something's equal to something. Yeah? Absolutely. The equal sign is going to bind. Nice catch. John, this is so much fun throwing candy. I got to say, we got to do this more often. All right, let me get to the point. What does an equal sign do? It is an assignment. It says, take this thing on the left and use it as a name to bind to the value on the right. It's not what I want here. Having already chosen to use equal as an assignment, I need something else to do comparison. And that's why I use double equals. Those two equal signs are saying, is this thing equal to, in value, the thing on the other side? Okay. Now, having done that, again, I want to stress this idea, and I'm going to write it out one more time, that there's a particular format here. So we have if, and that is followed by, and I'm going to use angle braces here just to indicate something goes in here. some test followed by a colon. That is followed by a block of instructions. And then we have an else followed by a colon and some other block of instructions. And I want you to get used to this. That colon is important. It identifies the start, and then the set of indented things identify all the things at the same level, and when we reset back to the previous level, that's when we go back to where we were. Okay. Now, that's a nice simple little test. Let's look at a couple of other examples to get a sense of what this will do. Again, let me comment this out. And let's look at this next little piece of code. All right? I'm binding z to be some value, and then I'm going to run this. Well, let's just run it and see what it does. Nothing. Okay, so why? Well, let's look at it. I'm doing a test there to say if the string x is less than the value of b, and x does not appear before b as strings, then I was going to do, a couple of things, because they're at the same block level. Given that that wasn't true, it did nothing. Now, wait a minute, you say, where's the else clause? And the answer is, I don't need one. All right, if this is purely a test of, if this is true, do this, otherwise, I don't care. I don't need the else clause in there to identify it. All right? Second thing I want to look at is, suppose I compare that to the one below it. Oops, that I don't want to do. I'm going to comment that out. And let's uncomment this. Again, I've still got a binding for z, and I'm doing the same test, but notice now I've got the two same commands, but they have different indentation. And in this case, in fact, I do get a different behavior. Why? Because that block identifies the set of things that I'm going to do if the test is true. If the test was not true, notice that that last command for print mum is now back at the same level of the ifs. So what this says is the if does the test. Having done the test, it decides I'm not going to do anything in the block below it. I'm going to skip down, therefore, to the next instruction at the same level as the if, which gets me to that second print statement. Okay, so now we're seeing some of these variations. Let's see what else can we do here. So let me try something a little more interesting, and then we'll get to writing some simple programs. So I'm going to comment those out. And let's go down to this piece of code. Let me uncomment it. Oh, yes, that was brilliant. Let's try this again. I want to uncomment that. I want to uncomment it again. All right, so here's a little piece of code that's going to print out the smallest value of 3. And notice what this is showing is that the ifs can be nested. Right? So if I looked at it, it's going to say if x is if x is less than y, then check to see if x is less than z. And if that's true, print out x is the smallest. And notice the structure of it. If it's not true, I'm going to go to that next else and print out the z is smallest. If the first test wasn't true, I'm going to skip that whole block and just go down and print out that y was smallest. So notice the nesting. I can flow my way through how those tests are actually going to take place. All right, so let's run this and see what happens. Great. Y smallest. Okay, is that code correct? Is that a tentative hand back there? Yeah.
It doesn't compare y.
Yeah, it's not doing all of the comparisons. Right? And let's just check this out because I want to make a point to this. Let's go back and do the following. Let's take y, change it to 13. Let's run it. So what did I miss here? 2 important points. First one, when I write a piece of code, especially code that has branches in it, when I design test case for that piece of code, I should try and have a specific test case for each possible path through the code. And by just doing that, I just spotted there's a bug here. And the bug was in my thinking. I did not look for all of the tests. So the way I can fix that is, let me comment, that out. Yeah. keep doing that. All right, we'll comment that out. And let's uncomment this. And notice the structure here. I now have multiple tests. So actually, let's just run it and then we'll talk about what it does. If I run this, yeah, I have a syntax error. Yes, indeed, because I forgot to comment that one out. All right. Thank you. And we'll try it again. Aha. And let's quickly look at the structure of this. This now has, gee, a funny thing. It says if x is less than y and x is less than z, then do something. And then it has this strange thing called elif, which is simply short for else if, in a second test. So the way to think about this in terms of flow is it starts with that if and it says check both of those things. And in that fact that both of those things is the fact that we're using a Boolean combination here. That is to say, we can take any logical expressions, combine them together with and, or not to make a complex expression, and use the value of that expression as my test. And that's literally what I've done there, right? I've got x less than y. That's a test. It returns a Boolean, which, by the way, is the other type that at least I would include here. It has only two values, which are true and false. And what that code says, if x is less than y, and logically, whatever I put up there, x is less than z, then the combination is true, and therefore I'm going to do something. So and is if both arguments are true, it's true. Or is if either argument is true, it's true. Not is if the argument is not true, it's true. And then the last piece, as I said, is I can now have a sequence of things I want to do. So if this is true, do something else. Otherwise, test and see if this is true, do something else. As many as I like, followed by at the end an else that says, here's what I want to do. Okay, now, having added this in, I have branching instructions. I have simple branching programs. These are still awfully simple, okay? And they're awfully simple because all I can do now is decide whether to execute some piece of code or another. Said a different way, in the case of the straight line programs, how long would it take to run a program? Well, basically, however many instructions I have, because I've got to do each one in order. With simple branching, how long is it going to take to run a piece of code? Well, at most, I'm going to execute each instruction once, right? Because the ifs are saying, if it's true, do this, otherwise skip by it. Therefore, for simple branching programs, the length of time, the complexity of the code is what we would call constant. That is, it's at most the length of the actual number of instructions. It doesn't depend on the input. Real simple programs. Let's take another simple example. Suppose I want to compute the average age of all the MIT faculty. It's about 1,000 of us. However I do that, I know that should inherently take more time than it takes to compute the average age of all the EECS faculty. There's only 125 of us. And that should take more time than what it takes to compute the average of John's and my age as instructors in 600, because there's only 2 of us. Right? Those pieces of code inherently involve something that does depend on the size of the input, or on the particular input. And that is a preface to an idea of computational complexity we're going to come back to. One of the things we want to help you do is identify the different classes of algorithms, what their costs are, and how you can map problems into the most efficient class to do the computation. Okay? Now, think for a second about computing the average age of the faculty. You can already kind of see what I want to do. I want to walk through some sequence of data structures, gathering up or doing the same thing, adding ages in until I get a total age and I divide by the number of faculty. How do I write a piece of code for that? Well, let's go back up to our original starting point of recipes. And I'm sure you don't remember it, but one of the things I had in my recipe is beat egg whites until stiff. Okay? That until is an important word. It's actually defining a test. Let me rephrase it into garbled English that'll lead more naturally into what I want to do. While the egg whites are not stiff, beat them. That is a different kind of structure. It has a test in it, which is that while something is true, do something, but I want to keep doing it. And so for that, we need to add one last thing, which is iteration. or loops. We're going to see variations of this. We're going to see a variation of it called recursion a little later on, but for now we're just going to talk about how do we do iterations. And I want to show you an example of this to lead to both the syntax and to the semantics. So let me comment that out. And let's go to this one. All right, what does this piece of code say? Not what does it do, but what does it say? Well, the first three statements are just assignment statements. I'm binding x, y, and iters left to some values. And then notice the structure. I got a keyword while. There's that color identifying it. And in parentheses, I have a test. I'm expecting the value of that test to be a Boolean, followed by a colon. The colon's identifying a block of code. And what this is saying is, gee, check to see if the variable iters left has a value greater than 0. If it does, then execute each of the instructions in that block. So I'm going to have an assignment of y. I'm going to have an assignment to iters left. I got a comment that I had borrowed in order to do some debugging. And then what do I want it to do? I want it to go back around to the test. And once again say, is that test true? If it is true, execute the sequence of instructions. So in fact, we can block this out and see what it does. If I make a little chart here, I got x, y, and iters left. X starts off as, and I set it up as here, I can't even read it, as x is 3, y is 0, iters left is 3. I can hand simulate it. It says, is the value of iters left greater than 0? Yes, it is. So execute those two instructions. It says take value of y and value in x, add them together, and create that as the new value of y. Right? That's the assignment statement. It says take iters left, subtract 1 from it, and bind that as the new value for iters left. Having reached the end of the block, go back up and check the test. Is iters left greater than 0? Yes, it is. So evaluate the same sequence of instructions again. Y plus x is 6. That's my new value of y. 2 minus 1 is 1. That's my new value of iters left. Go back up. Is iters left greater than 0? Yes, it is. So once more, thank God I didn't take 47 as the example. X plus y, subtract 1 from iters left. Go back up to the test. Is iters left's value greater than 0? No, it is not. Therefore, skip the rest of that block of code and go to the next instruction, which is, print out y. And in fact, if we test this, son of a gun. Got a simple square procedure, right? It's just squaring an integer is what it's doing. But notice the structure. Now I have the ability to create a loop. That is to reuse the same pieces of code over and over again as I go around. And this adds now a lot of power to the kinds of code I can write. Notice some other things I want to highlight on this. Right? The first one is that test has to involve, or shouldn't have to, but almost always is going to involve the value of some variable. What if I don't change the value of that variable inside of the code? Or another way of saying it is, what if I did this? Comment it out. What happens if I run this sucker? Yeah. It'll go forever. Absolutely, right? It's going to loop into an infinite loop. I think I can hit this close. No, I can't. Boy, what a terrible aim. Right? Try again. The point I'm trying to make here, thank God we're at the end of this lecture, my tongue is falling apart. The point I'm trying to make is that test needs to involve some loop variable that is changing. Otherwise, the test is always going to be true. We're going to go off forever. This would loop forever if I did that. Right? Second question, or maybe a better way of saying it is, the general format you're likely to see here is a test involving a variable name which must be initialized outside of the loop and which interior to the loop gets changed so that the test is going to change. Here's the second question. What value of inputs, what values of x will this run correctly for? Probably should be integers, right? Otherwise, this is going to be doing something strange. But all integers? All right, suppose I do this. This is my last example. Yeah, how about that, right? We knew this was trying to do squaring, so intellectually we know we can square minus 4. It ought to be 16, but what happens here? Double fudge knuckle, right? It's going to run through the loop, accumulating the answers, but because I'm subtracting, it's just going to keep making x more and more negative as it goes along. Again, it's off into an infinite loop. which is a way of reminding you that I need to think as I write the code about what are my expectations on the input and how might I enforce them. In this case, I probably want to make sure I use absolute value of x before I carry it on. Yes, ma'am? Sorry, say it again? Oh, you're absolutely right. Because I bind iters left to, yes, thank you. Boy, too candy for you. You caught me making an error. Yes, the point is, it's not going to work. She caught both of them, impressive. It's not going to work because iters left is already negative. It's just going to skip the whole loop, and I'm in trouble. So thank you for catching that. All right, I was going to do one more example, but I've run you up to the end of the time. I'll leave the example on the handout. It shows you another version that we'll come back to next time. The key thing to notice is I now have the ability to create iterations, which extends what I can do. And we'll see you next time.